From Photonics Media, this is All Things Photonics, a podcast shedding light on industry-shaping advancements in lasers, optics, imaging, metrology, and sensing. Each episode, our hosts speak with luminaries, rising stars, and market leaders about the trends shaping the current and future landscape of photonics. From space and deep-sea exploration to precision timekeeping and advanced manufacturing, this is the podcast for progress on All Things Photonics. This season of All Things Photonics is brought to you by Polyscience and Thor Labs.
Today's episode is brought to you by Polyscience. For over 60 years, the Polyscience line of award-winning temperature control equipment has been helping the photonics industry reach its goals safely and efficiently. Our products are made in America and delivered globally. Please visit polyscience.com to learn how we can help you. Changing the world of chillers is more than a tagline. It's a part of our history. Today's episode is also brought to you by Thor Labs, a global designer and manufacturer of photonics technologies. We provide a comprehensive portfolio of over 22,000 stocked items for same-day shipment, complemented by endless custom solutions enabled by our vertical integration. Visit thorlabs.com to learn more.
In today's episode of All Things Photonics, we begin with an interview with David Shelton, President and CEO of AmeriCOM. AmeriCOM, the American Center for Optics Manufacturing, is engaged in efforts to advance American leadership in precision optics manufacturing through research and workforce development initiatives. Shelton, whose background lies in infrared detection and metamaterials, joined as President and CEO in April of this year. Following our interview with Shelton, we'll speak with Andrea Alù, the Einstein Professor of Physics at the City University of New York. Most famous for his work in developing invisibility cloaking technologies, Alù is one of the foremost experts in metamaterials and metasurfaces. Our conversation gives a primer on metamaterials, their potential, the limits of invisibility, and a look to the future of metamaterial and metasurface technology. First, Senior Editor Joe Kosinski speaks with AmeriCOM CEO Dave Shelton.
This is Joe Kosinski, a Senior Editor with Photonics Spectra on the All Things Photonics podcast, and I'm joined today with Dave Shelton, President and CEO of AmeriCOM. Dave, thank you so much for joining us.
Yeah, sure.
Well, let me get right into it. So recently, a big announcement from AmeriCOM detailing a 3-part phase to engage the optics industry and support the U.S. military, focusing on research programs, lab facilities, and the Defense Precision Optics Consortium. Can you kind of break down the steps in this process or tell us about the strategy to implement this?
So it was always part of the original AmeriCOM mission. So I've been here for about 6 months now. They had replaced the previous CEO that had been with the company from its start, and there was kind of a hiring process to hire me that started. I think they first reached out to me back in, I want to say it was like January or February of this year. By the time I actually came to interview was, I think, in early March, and it went pretty fast from there. And then I started right at the beginning of April, I think like the day after the eclipse.
Yeah, so something special in the works.
Originally, it was going to be the day of the eclipse, and then we ended up moving it back because that was like in Rochester, at least like a national holiday. Although it ended up being, I think about in the 6 months I've been in Rochester, that was about the most overcast day we ever had was the day of the eclipse. So terribly ironic. It got dark out though. That was cool, but I'm glad I didn't travel up here just for that. But yeah, so when I started, I kind of, and I knew from the beginning before I came here, I wanted to see the original proposal. I mean, so what is AmeriCOM right now is really mostly just a single contract with a Department of Defense entity there's kind of a hierarchy. So there's the Office of Secretary of Defense, which oversees, Army, Navy, Air Force. There are Undersecretary of Defense that are under the, OSD, and then a lot of the Undersecretary of Defenses are broken into multiple offices down from there. So there's an Assistant Secretary of Defense under one of the Undersecretary of Defenses. So three layer. It's like a Russian nesting doll thing. So 3 layers in now, but there is an office under the Assistant Secretary of Defense, I think, for Industrial Policy called the Industrial Base Analysis and Sustainment Office. So that's who AmeriCOM really works for and is currently funded under. Now we're working on expanding that beyond that. Really, AmeriCOM is a not-for-profit that does work under a contract with IBAS. So we're not, I know sometimes there's confusion. AmeriCOM is not, we're not a government agency. We're not government employees. We're really just a government contractor. And we do happen to be a 501c not-for-profit. So the AmeriCOM effort was split between workforce development, which had been undergoing for some time now, and we've had a number of workforce development programs related to train optics technicians that we've started around the country. And so that had been going, and there was this thing called the Defense Precision Optics Consortium, which had just not really gotten off the ground that much. There weren't any, consortium implies consortiums have members. There weren't any members when I started. So that's really what we started launching a couple months ago now, is sort of our drive for what the DPOC is going to be, how you become a member, why you would want to become a member. The good news about that, it's free. It's free to join right now. I mean, we don't really have anything to offer for, but the benefits to joining, we have a couple key issues related to the defense in particular, supply chain, but I would say it impacts probably a lot of these things are dual use. So there's a lot of impacts to commercial stuff as well. But that's kind of what our focus has been. And then we also have, as part of the Defense Precision Optics Consortium, there's a lab that is in Fairport, New York. So we're just sort of east of Rochester, just outside of town. We have a lab that we've been standing up here that is essentially optics fabrication and metrology equipment. And we're making that available to the industry as something like a semi-user lab. And I call it a semi-user lab because we're really sort of modeling it off of what's done in the semiconductor industry with things like the National Nanotechnology Infrastructure Network, which might be defunct right now. But back when I was, 20 years ago or so, that was a thing that was a nationwide network between Cornell, Georgia Tech, Stanford, a number of other schools that had just really high-end clean rooms that you could do a lot of really cool prototype working projects for semiconductor processing. And it was a really enabling thing if you were a small company and you probably didn't have the resources to fully capitalize and to be able to buy all that equipment yourself. But if you had some projects, you could probably pay by the hour to use tools. And so that's what we've done with this facility here in Fairport. All the tools that we have are available at hourly rates, which I believe are now all published on our website. If that's not up yet, they will be very soon because the rates all exist. I've approved them. I've seen at least a draft of the webpage. I'm just not sure if it's actually gone live. So if it's not there, it will be there very soon. You can just go to AmeriCOM.org, and there should be a link there for the DPOC or DPOC. So that's where all of that is published. And so we're able to do work on whether it can be either commercial or government projects. But we've got a list of tools. Essentially, it's grinding and polishing, it's diamond turning, and then it's a whole bunch of metrology for optics fabrication. So all of those tools, we've got tools that go to 5-axis and movement, so we can do spherical, aspherical, and freeform optics. The tools are big enough to be able to handle potentially large diameters. So something as large as like 10 inches in diameters, I think maybe up to 12 inches even. Defense projects, somebody was asking me the other day why some of these defense systems aren't more miniaturized. And it's like, well, defense stuff, you're pretty much always trying to see something that's very far away for some reason or another. the best way to see something very far away is well, you need a large entrance pupil. There's kind of just the laws of physics and radiometry demand it. There's no way around it. So defense stuff, you need large entrance pupil. That means you're going to need large optics. And so that's why we kind of built it that way, because it does definitely have a defense kind of priority and orientation. But really, this whole IBAS prototype project, the reason that the military invested in it, the reason that Congress supported it, it was always intended to be really sort of an investment, and so the government wants to see a return on investment. So this thing is supposed to become sustainable. It's supposed to stand up on its own. It's not supposed to just keep having, government money being the only thing that sustains it. So we're very interested in working with industry. And we've got, I said semi-user, unlike semiconductor processing tools, it's probably not going to be send your grad students and we'll just turn them loose after like an hour of training. Some of these tools are more complicated than that. And there's also like some safety issues that you don't always necessarily have in semiconductor processing. But you are welcome to, and I think really what the benefit, it's a 10,000 square foot facility. It's only so big. We only have so many tools. So it's not like this is going to take over anybody's production process or anything. But if you're looking to do prototype work, if you're looking to try something out, and this is of a lot of interest and benefit to the tool manufacturers as well, which we're always looking for. If you want a place to demo something, there's a lot of value to. These tools are all. They range in price from $300,000 on the lower end to some of them are more like $1 million tools. If you're, as a company, going to make an investment like that because there's a production program that you want to support, it would seem to me like you'd really like to try it a few times first. And so this provides an opportunity to do that. So potentially it can be used as a showroom. We also have some plans. We haven't started it yet, but there is an intention for it to be a venue for short courses. We've got both the conference room space here, as well as the tools, and there'd probably be. We're probably talking here like week-long short courses where you might have something like a dozen students at a time. But it's a great way to augment some of our workforce development programs, like here in Rochester, for example. Monroe Community College actually does have some pretty advanced CNC tools and optics fabrication equipment. Anywhere else in the country, any of the programs that we've stand up don't have anywhere near as advanced equipment as what MCC has. They, in a lot of cases, have some fairly basic grind and polish type equipment, but not as advanced. Like if you wanted to, learn how to produce freeforms or something like that. That capability doesn't really exist. And so this, from our program at Front Range Community College in Colorado, or Sussex County in New Jersey, or Valencia in Florida, or Keene, New Hampshire, or a number of the other programs that we're still in the process of trying to start up, you could learn all the basics and get your 1-year degree, and then there could be maybe a micro credential or something that you could get from a 1-week short course where you come and you actually do some freeform optics processing, like a diamond turning tool or a high-end polisher or something like that. Mm-hmm. So I think there's a lot of, again, MCC itself, I think, has a lot of that stuff, but elsewhere in the country, people are not usually so advanced. Right. So that's kind of the opportunity there. And then in terms of the research issues that we're pushing, we have 3 kind of main thrusts. The first one is automation of especially the fabrication of kind of less complicated and lower cost optics. So we're talking here, and again, this is all defense oriented. So defense markets where you have a lot of volume. You're not talking space systems or airborne systems. You're probably talking maybe ground vehicles, but probably where there's really big numbers is when you get to dismounted infantry. And so now you're thinking things like rifle sights, you're thinking things like night vision goggles. It's going to be something that somebody's either carrying or it's mounted to their helmet, one or the other. And there's a lot of visible optics in some of those things. And you're talking market sizes where the Department of Defense potentially needs to buy these assemblies on the order of like maybe 10,000 a month. So really pretty high numbers and potentially a lot of cost. And we're talking mostly spherical optics, something like 1 to 2 inches in diameter. So nothing particularly high tech in any way. But in something like a rifle sight, for example, you may have 15, 20 different optical elements that are part of that. And while a lot of the assemblies are done in the United States, they do have to rely on components which are sourced from overseas. And so, and usually largely for Asia. And so there's a potential supply chain risk there. And this is the common theme of, what is IBAS as an organization interested in, are what are the, supply chain weak points? What are the bottlenecks? In the event of some kind of crisis, if we really needed to field optical sensors quickly, what are the things that limit our ability to do that? So the cost of and the schedule of related to touch labor is certainly one of those things. We know that a lot of what wire it's optical component manufacturing in the United States, especially some of these lower tech things, they're 3 to 4 times more expensive here than they might be from an Asian market. But that difference is mostly just driven by the difference in the cost of touch labor. So if we can improve the automation of these tools, you can get the same technician now. It's not that we're going to get rid of technicians. You still need people to run things. There's going to be problems. You need to be watching what the computer's doing. So it really is just another tool. But that additional automation and having a better tool, now the same technician can do 3 or 4 things at once, as opposed to having to focus all of his attention on just a single task. That increases their productivity, which is great from the perspective of optics technicians, because the more productive you can make them, the more valuable they become, so the more they get paid. From a workforce development perspective, we're always very interested in, what an optics technician gets paid compared to other professions, because we do, like to think of this as being a better career compared to, because it's a career that doesn't take usually much more than an associate's degree. So you're looking at other career paths that have similar levels of training, and we would really like it to be the case that optics is is a better thing to go into rather than, say, I don't know, managing a convenience store.
Yeah, and I'm glad you mentioned that too, because optics definitely an expanding industry, but it's such a global industry too, and it'd be nice to keep the work at home. I think is a definite domestic goal. But like our American workforce is expanding fast enough to kind of keep up with this demand. And, what can AmeriCOM do to kind of help get more people into this field?
Well, yeah. So our workforce development work is entirely driving that. And there's a strong marketing component to it. A lot of it is there's always there's a lot of misconceptions about what optics is. Like most average people, if you say to them that I'm going to go work in optics, they think that you're making eyeglasses. Like that's what the average person, when they think of optics, and so a lot of times, instead of saying optics, we'll use words like photonics, or we'll talk about lasers a lot of times. Even like we slap the word laser on stuff, even when there's not necessarily any lasers involved. A lot of, especially in the defense world, a lot of optical systems are entirely passive. There's no laser anywhere involved.
But it piques interest, right?
Yeah, because lasers are cool. I mean, and as soon as you say lasers, people are they're thinking of the right type of thing. And the other in Rochester, the term that we always use is precision optics. And so that's really the precision optics. You're talking about tighter tolerances and a lot bigger apertures and more complicated things than what just goes into eyeglasses. And it's a very different volume. Precision optics they're a lot harder to make, and there's a lot fewer of them compared to eyeglasses, where the market size is enormous because, I don't know, some huge fraction of the population needs corrective vision in some way. So that is a massive market. It's a very different market from what we mean by precision optics, which is targeted to defense is one thing, but there's a lot of other markets that are part of defense precision optics. Like right now, semiconductor processing equipment is one of the really big areas. Those are mostly high-end photolithography equipment. So this is all stuff that's UV, and it's always pushing to shorter and shorter wavelengths to get smaller and smaller. Semiconductor nodes, with everything that's going on right now with the CHIPS Act and a lot of the interest in the country to bring semiconductor processing back onshore, that's generating a whole bunch of semiconductor processing tools being built by companies like ASML, for example. And they need an awful lot of optics technicians in that industry. So that's really right now, I think, in the defense precision optics industry, that's probably the biggest market. It's bigger than defense. Defense is maybe a little bit more sustainable. Defense products and markets kind of come and go, but there's always something going on. The semiconductor processing stuff is a big push right now. To what degree that'll still be a big thing 5 years ago, I think kind of remains to be seen. But certainly for at least the next few years, that's a real major driver of the industry. But yeah, but getting more people, interested in it as a career path, I'd say the biggest thing is really just raising awareness, just because it's not a thing that the average person is familiar with. Most people, if you take like your average high school student, they may not have any sort of exposure to anything to do with optics in their high school career. Maybe if they had high school physics, which not everybody takes physics in high school, it's an elective. It's generally not mandatory, and lots of people take biology or chemistry instead. High school physics is probably the only place you would encounter optics, and even then, it's by no means certain. You might be learning more like, Newton's laws of motion and F equals ma, and you might not ever really learn anything about optics necessarily. And, exposure from normal media is minimal, or it's kind of all over the place. So we have the futureisoptics.com, or Future is Optics. It's part of the AmeriCOM marketing campaign. But that's a lot of the work that our marketing team has done as part of the IBAS contract, is to really raise the awareness of optics as a career path and optics technician as a career path. And the great thing about, and really the reason that we've done all this work with the community colleges as kind of because even if you just get a 1-year certificate, but you got that from an accredited community college, so it's 1 year. So, okay, well, now you're like halfway towards an associate's degree. If you get an associate's degree, you're halfway towards a bachelor's degree. So it gives you some upward mobility that, if you start out as an optics technician and you find out that you like it. I've met a lot of people that have started their career as a technician, and there really is a growth path. You can start your career as a technician and you can finish your career in management or in engineering or some other role. And so there's opportunities for upward mobility that you probably don't have if you, for example, go work for Starbucks. I mean, I'm not really sure where there is to go with that necessarily, but I think the idea and a lot of the sales push for why should you, consider a career in optics is because it gives you a lot of interesting paths that you can go down. In addition to what the starting salary would be, which I think is usually pretty competitive, but I don't think the starting salary would be purely the reason that you go into it. I think you go into it because it interests you. It's work that you find enjoyable. There's something very, zen about fabricating optics and grinding and polishing lenses. I mean, it's the tools don't talk back and yell at you or anything, which is better than a customer service staff job. So it can be, aside from the starting pay, it can be a rewarding career field. And so I think that's a lot of the pitch for, and optics are all around us in so many different ways. I mean, there's so much modern communication stuff is based on fiber optics. So beyond the defense stuff, there's so many, jobs. There's so many dual use technologies. A lot of optical technologies have started out as some kind of, defense related research project, and it's found its way into some kind of commercial market. The government loves dual use stuff. They like to push that, and for very good reason, because anything that's made exclusively for the Department of Defense is going to be really, really expensive because the market's going to be small. And the only way that you ever make stuff affordable is you have to get to a larger market. And so and the government knows that. And so there's always an imperative to push for and search if there's a way to make something dual use. That is always going to be the government's preference because it's the only way things become affordable.
Got you. And to focus on defense, because it is such a big driver in this and in many markets, what are the kind of the growing threats facing America, other nations, and how can optics and AmeriCOM, work to provide solution to these threats?
So it's an interesting, there's a lot of things going on in the world right now between what's going on in Ukraine. There's a lot of tension over Taiwan. So I think we're all aware, if you've watched the news lately, you know that the world has become a very dangerous place. I think one of the trends that has been occurring for some time now is if you go back to in a military engagement, the game is mostly if you're trying to establish air superiority, let's say. And so it comes down to roughly something like, well, if I can see you before you can see me, and if I can affect you in some way before you even know that I'm there, that's how I win. And really, whether it's an air superiority thing, whether it's a ground mission, you look at almost any kind of military mission, and that's kind of what it comes down to. So just obviously, we're always trying to detect, potential threats and potential adversaries from further and further away. There's nothing secret about that. I think it's just kind of common sense. So, okay, so you can do that type of mission either with a radar-based system or some kind of radio frequency type system, which is the older way of doing it. We've been doing that type of stuff since World War II. Radar really became common. There's always been, we've had telescopes forever, but even through the Cold War, radar was really kind of the most important thing optical sensors have really been started to be deployed more and more going back to, the 70s and 80s, especially in the infrared, is really of importance to the military for some basic reasons, like in thermal imaging bands, for example, anything that's relatively warm is going to emit more than the background, and so it just naturally stands out. Military sensing is always all about discrimination. There's lots of natural ways that imaging in the infrared band lends itself very well to discrimination. So, I need to tell, I've got all these different things that I don't care about going on, but then there's this one thing that's moving fast and it might be a threat. In the infrared, I can ignore all the background stuff and really focus in on the one kind of piece of salient information that I really care about. And that's why the military has always, even going back to World War II, is when this really started. Starting to use thermal imaging sensors and infrared sensors for various types of detection missions. And it was, in World War II, it was very much a novelty. And then even moving forward, it became more and more important. And in modern warfare today, it's really become quite critical because everybody has gotten a lot better at electronic warfare. You can read in the newspaper a lot about the idea of radar-denied environments. You can read about what happens if GPS gets denied. Any kind of radar thing is easier to jam generally than an optical sensor is. So optical sensors have become very important to the military for everything from navigation to threat warning to trying to find potential targets and threats at longer ranges. And that's really been the big change compared to the Cold War and potentially previous conflicts. If a conflict were to happen in the near future, I would say that optical sensors are going to be more important than they've ever been before. And so that's why I think, there's a lot of emphasis on it, because it's a more important piece of national security than it probably has been at any other time in history.
And you mentioned too protecting airspace, and we've seen, you can turn on the news and, like you said, you can see, drones or things, being plucked out of the sky, and that's something where you see it first, you react first, you take it out, so that threat is neutralized. So, what goes into the process of guarding the airways, of spotting, threats, and these are not just slow moving, unmanned vehicles. These are things zooming through the sky, and yet, with enough powerful optics with precision, they can be just plucked out of the sky and just kind of neutralized.
Yeah, and I know I've had I've had a chance to go and talk to a lot of optics companies recently, and I know some of the companies I talk to are, they don't really want to be involved in making weapons, or they don't want to build anything that hurts people. It's like, well, I entirely appreciate that. I don't either. With advanced optical sensors, most of what we're trying to do is you're trying to stop a fast moving threat, like some kind of unmanned drone or some kind of missile or something like that. And essentially what you're trying to do in that type of scenario is you're trying to shoot down a bullet or something that's actually moving a lot faster than the bullet, and you're trying to do that with effectively another bullet. That's really hard. That's really, really hard to do. I mean, it's, affecting something that's not moving is easy. Shooting a bullet out of the sky with another bullet is really difficult. And that's a lot of these advanced optical sensors, that's the kind of thing that they're trying to do. And so they have to be able to respond really quickly. They have to be very sensitive. There's a lot of things that goes into that type of mission. And ultimately that's what most defense sensors, that's what they're trying to accomplish. And you can read about them being used in Israel, they're being used in Ukraine. Anywhere where there's any kind of modern conflict going on, these things are all being used. But they're really, it's much more of a mission to protect civilians, to protect critical infrastructure. I think there's more of that than anything that's necessarily offensive. Offensive is kind of a lot easier than to shoot down a bullet with another bullet. That's what's hard.
Sure, yeah, to hit this giant stationary target, stationary, right? But then the defense is to say, they're trying to shoot our stationary target. How do we, pluck it out of the sky going, X amount of miles an hour and do so with precision? We talked a lot about, what AmeriCOM is doing to recruit domestic companies for research to attract more students. But it is a global market, and naturally defense is a very sensitive kind of topic. How can we work with other global partners to, advance our goals and advance our defense systems, but at the same time protecting our defense systems, because naturally sharing of information can be very delicate.
So the way that all of that works is, I would say that overall that is definitely a thing that the government is in charge of. But what they don't do is allow people like me to make any sort of decision about what gets shared with whom. And so it's not that, like, I would say overall, like as a country, yeah, we're really interested in that. We have, sort of different tiers of allies, and there's a lot of, especially amongst like NATO countries, for example, there's definitely a lot of joint development work that certainly does go on. This is no different. I mean, any NATO country is going to have the same sort of export restrictions. So usually anything, if it is developed under a defense contract, the IP associated with that probably becomes ITAR, which is International Trade in Arms Regulations. So if you're going to export any of that type of stuff, it's possible, but the decision isn't up to you. If it's ITAR, you have to go to the State Department and you have to get a license. If it's there's other things that are just regulated by the Department of Commerce. But overall, the theme and the work that we do with AmeriCOM, there's nothing saying that we can't work with international companies on a project or something like that. But in order for me to do so, I don't have the authority to unilaterally decide that I can. I have to get permission from the government in order to do so. So it's not that it's not possible. And it's not that the government's not interested in it, but they do hold to themselves the authority to make all those sorts of decisions. And people like me don't get to. We can ask permission, but that's all I can do is ask permission. I have no deciding authority for anything like that.
Sure, yeah, naturally a system of checks and, background, reviews just to make sure everything is square. I'm sure a very thorough process. And again, we're dealing with such sensitive things that it's not going to be something taken lightly to share defense strategy or information with just any foreign entity.
Right. Oh, yeah. I don't decide any kind of strategy. I just try to interpret requirements.
Fair enough.
Way above my pay grade.
Right. Well, let me ask you too. This is kind of a broad blanket question, but I think it starts a good conversation. Where do you see the optics industry in 5 years? With it's like you said, it's going to be a huge part of future conflicts. It's in the technology all around us, in our pockets, in our cell phones. Is it it's not easy to predict, but growing so fast, can you forecast what we might expect in the next few years?
On the commercial side, I mean, so optics that are difficult are either optics that are really small, like think of what goes into like optics the size of what goes into your cell phone. And there's a really big market for all that type of stuff. And then the other thing that's really difficult is optics that are very large. So optics that are very large are, I mean, mostly just you're talking about some kind of telescope. So you're either going to be using a telescope. There are, a lot of civil space, the work that NASA does. There's things like the Roman Space Telescope. And then there's defense type applications where you're, for whatever reason, you're trying to see something really far away. And like I said before, those are, anytime you're trying to do something like that, the amount of signal and noise that you get is entirely, I mean, the easiest way to improve it is to increase the size of your entrance pupil. That's why the James Webb Space Telescope is trying to see stuff that's incredibly far away. So it's got that massive aperture that, all those mirrors that fold out to make that big thing. I mean, that's so big because it's trying to do something that's really, really challenging. So that's difficult. And this has been a trend that has been kind of slowly coming for a long time. But I think particularly with things like thermal imaging, I think there's a lot of opportunities for machine vision and for industrial processing. With infrared stuff in particular, I think there's a lot of growth. And I'm thinking things like camera modules, not stuff that's trying to see necessarily that far away, but it's just governing some kind of industrial process. And with infrared imaging in particular, it's almost kind of like a novelty and a niche for a human being to be looking at thermal images. Most applications are, there's not a human being looking at an image, but there's some kind of image processing algorithm that's running in real time, and it's trying to pull salient information out of imagery. And then what's getting communicated to the human is really just that salient information. And so that's the way most defense sensors work. If you're a threat warning sensor, for example, a threat warning sensor is literally, it's got a camera and it's just sitting there and it's got some frame rate and it's like essentially taking video. But there's an algorithm that's running against that video and it's finding that, there's this thing out here and it's a threat. And Mr. Pilot, man, you should be aware that this thing is out there. And what it tells you is that there's this thing over here and it's at some angle and it's at maybe some range or whatever it is. Machine vision is the same kind of idea. And whether it's, guiding robotic stuff around automatically or it's improving manufacturing processes. If you're semiconductor processing, for example, anytime that in circuits when you get a hot spot, that probably indicates a problem is going to occur. And so you're probably going to see that in a thermal image sooner than you would ever necessarily see it in the visible. And so you can have stuff whizzing down the line. And if you have a fast frame rate camera, you can be taking images really fast. You can be doing computations. And then when your image processing algorithm sees a problem, it can alert the operator that something has gone wrong on the manufacturing line. We've had projects in the past where we've been looking at things like train wheels, train derailment. I mean, there's been a couple of cases just in the United States in recent years where train derailment has led to a huge environmental disaster. This is a problem that happens all over the world, really, using thermal imaging to look for hotspots on train wheels, and you can do that in real time and kind of monitor things so that you can see, there's this hotspot that's starting to emerge, and if you can find that, then you can correct the problem before a massive failure occurs. And so there's all kinds of industrial processing type opportunities, and things that you can look for with thermal imaging. And there's kind of, that we used to talk, I don't know if it gets talked as much now as it used to, but the idea of the Internet of Things, that you would have all of these interconnected sensors that would be constantly relaying information back to some kind of user, but it's like there's a tremendous amount of data. And so I think a lot of the future is all these different cameras and sensors, optical sensors, that are collecting all this different type of data, but it's really much more for algorithms to interpret in some kind of machine vision type application. Even in things like security and surveillance, you could put something that is critical that you don't want somebody messing with, like a power plant, for example. Well, you could put cameras all around that thing, but then if you have to take a human being and have them just sit there and watch all of these cameras for hours at a time, they're going to miss stuff because we have limited attention spans. It's hard. When hours and hours and days go by and nothing ever happens, when something finally does, you're liable to miss it. A machine-based vision algorithm can probably do a lot better, but you have to be able to control the false alarms. That's all of these things. There's always a receiver operating characteristic that's your probability of detection versus your false alarm rate. You don't want, if you start having false alarms, the whole system becomes useless because you'll just ignore it. But if you miss stuff, that's a problem too. So all these types of machine vision applications, it usually comes down to some kind of receiver operating characteristic that you're trying to define. But I think that's where a lot of the future is in those types of applications. It's not, the idea of humans just looking at pictures in real time we've been doing that for a long time. I think the future is much more machine vision.
Now, is that something where AI could be playing a bigger role to kind of see these processes, to evaluate them, and to
you can call it AI. A lot of this stuff is, that's kind of the fancy buzzword that we like. Image processing and algorithms and stuff like that have been around for a long time. It's not necessarily anything new, but a lot of the more modern algorithms and architectures that you could implement do have very much, because and with imagery, you can develop such large data sets. So you talk about training algorithms, you talk about AI and machine learning, but absolutely, it's all sort of the same thing. I think that's a lot of AI stuff is based around interpreting images in some way.
All right. Dave Shelton, President and CEO of AmeriCOM, thank you so much for joining us on the All Things Photonics podcast. Really appreciate you giving us the time.
Oh, you're very welcome.
Today's episode is brought to you by Avantes. Unlock the power of light with Avantes. For over 30 years, we've delivered precision fiber optic spectroscopy, trusted for custom integration and reliable data. Discover how to empower your application, industrial, scientific, or beyond. Visit Avantes.com and experience spectroscopy solutions that innovate. Today's episode is also brought to you by LightPath Technologies. From concept through prototyping, volume production, and global distribution, LightPath has the optical knowledge and manufacturing expertise to be your optics partner every step of the way. Visit lightpath.com to learn more.
Up next, news editor Joel Williams speaks with Andrea Alù, Einstein Professor of Physics at the City University of New York. So, in preparing for this interview, one of the things that I struggled with was, how do we dip our toes into metamaterials and metasurfaces without sort of falling down a rabbit hole really quickly? I imagine this is something that you have a lot of experience with, since you have to answer the same question everybody else does when meeting new people. What do you do for a living? I imagine that, after somebody hears, I'm a professor or I'm a researcher, they have some follow-up questions. So I'm interested in how you answer those questions. Namely, what are metamaterials? How did you get into that field? And what do you enjoy about it?
Yeah, that's a great question, by the way. Yeah, and I do receive it quite a lot. Metamaterials are engineered materials that try to fight the conventional limitations of natural materials. So several years ago, and this is actually an old field in practice, since the start of the field of artificial materials, probably in the beginning of the 1900s, there has been a lot of interest in trying to make up our own materials to interact in an efficient way with electromagnetic waves, with light, with sound. This typically has been driven by technology demands. The technologies that we use today for optics, for radio waves, for instance, for radar technologies, or for sound, are all relying on a pretty limited set of materials. And typically materials do not come optimized for a certain functionality, a certain property in their interactions with the wave of interest, with the frequency of interest, with the intensity of interest. So over the years, scientists and engineers have realized that if you can structure your materials, you can provide, you can change quite dramatically the way in which they interact with waves. This is actually a field that is rather old. In fact, in biology, there are many examples of this structural functionality, structural colors, for instance. The bright colors of the butterfly wings come from not from chemical composition of materials, but from nanostructures or microstructures that change the way in which light bounces off the wings or of some insects or the body of certain animals or certain insects or birds. So basically what we do is bringing this to the extreme and try to, first of all, understand what are the actual fundamental limits of interacting with waves through materials. And second, can we actually build materials that operate at this limit for the application of interest? So my work is really driven by curiosity, is really driven by questions about what if or what can we actually achieve in practice. And I'm lucky to be in a very well-equipped center for research that actually drives this type of explorations. We have a very well-equipped nanofab that can structure materials at the nanoscale, so we can make our materials. We have very talented group of collaborators, scientists, students, and postdocs that can design and optimize the structures, can ask these fundamental questions of what is the limit, and then we can test these materials in our laboratories. We characterize them for different applications, and also we have a network of collaborators in industry and in research labs that can push them to the next step in terms of application for technologies or transition into systems or devices that can use them for energy, for sensing. The interesting aspect of metamaterials, the reason why there's so much on the spotlight these days, is that many of our technologies today rely on wave-matter interactions. If you think of wireless communication systems, it's all about taking waves, adding information onto them and transmitting them from one user to another. Energy, green energy in particular, is all about trying to extract energy from waves, from light, from ocean waves, from mechanical waves in the context of wind. Similarly, for sensing, imaging, biomedical explorations, the field of photonics, or in general the field of light and optics, is fundamental to this explorations. It's really the bridge that allows scientists to explore the next opportunities for medicine and biology, and also the field of computing from both classical and quantum computing relies heavily on photonics, on wave physics, on interactions of radio frequency signals with superconducting elements. And all of these fundamentally requires optimized structures and material responses.
Excellent. So sticking with the theme of commonly asked questions, one of the things that you're famous for is your work developing cloaking technology. And so what I'm curious about is, how did that project begin? Was there a specific point for you where the idea of invisibility kind of crossed over into the realm of possibility? And if so, what was that like?
Absolutely. Yeah, that were all days the start of really the explosion of interest around metamaterials. I was working in the group of Professor Neder Engeta at the University of Pennsylvania. And again, he's a master of this curiosity-driven research. So when I was in his group, we were exploring what are the fundamental limits on scattering. Scattering is the process through which an object distributes or scatters around the energy that comes in the form of electromagnetic waves or sound waves. In fact, we were looking at the opposite process. That is there an opportunity to actually scatter a lot from a very small object? So opposite to invisibility, making something very bright that actually is not really visible. And I remember I was studying this fundamentally, mathematically, these opportunities and what happens if the material properties in terms of electromagnetic response become different from the usual ones that nature provides us. The years before, there was a lot of interest around the first realization of a negative index material, a material that has an index of refraction that has an opposite sign to what regular materials have. And we were wondering, what if we make an object out of this strange material? And in exploring these opportunities and different geometries, I bumped into this curious opportunity for which materials with unusual electromagnetic responses put around a regular object would actually compensate for the scattering, would provide some form of negative scattering that cancels, interferes destructively with the scattering of the object itself. And discussing it with Professor Engeta, we came up with what I believe was the first paper or proposal. It was a theory paper of using these unusual materials for suppressing the visibility or the detectability of an object to a radar or to a laser or to an optical source or even acoustic source. Since then, we've done experiments, we've demonstrated this phenomena, but I think, again, going back to the question of limits and of what can we do or what if we have these materials, we've also realized over the years that there are fundamental constraints as to what you can do in the realm of invisibility. And that's an example that is very instructive, because it's also what I teach to my students and postdocs, that over and over many years now, that original paper was about 20 years ago. But we keep bumping into the same idea or same process in which we ask a curiosity-driven question. We're very excited about the opportunity that comes from these new material properties. But also what is important to realize is that the physics always has a limitation. We can push the limits of kind of conventional wave physics, but it's also very exciting to explore what are the new limits or what you can actually do or not do. In fact, more recently, we have shown in a couple of theory papers that there are fundamental limits on the size of an object that you want to hide compared to the wavelength of excitation, or to the bandwidth, or the basically spectrum of wavelengths over which this invisibility comes in, or also the degree at which the object is hidden. And we have also proposed ways to somehow push the boundaries forward, for instance, by using active elements or nonlinear elements. But we're also facing the issues that anything you add to the picture imposes new limits. At some point, you can push the boundaries, but you always have to realize that the explorations lead you to other opportunities, but also other fundamental constraints. Right?
Interesting. I hesitate to ask the question because we only have so much that we can fit into the interview, but I am curious about the what you said about the size of the object that you can conceal. Very briefly, could you kind of explain what factors into that those limitations? Like,
absolutely. Actually, it's easy even to think about this from a fundamental point of view. We are very familiar with the fact that we cannot transmit information faster than the velocity of light. This is a fundamental causality principle that spans across all ways of physics. If you have an object, especially if the object is impenetrable, so think, for instance, of our body, light cannot travel through the body. So a cloak of invisibility would work in a way of routing light rays that would bounce off our body around us and to the back to avoid shadow. And by the way, as a disclaimer, our theory and our experiments are trying to realize a full cloak of invisibility. That means something that makes us fully transparent to the impinging wave. There are other ways to conceal an object that are have much more relaxed constraints. Houdini, for instance, was a very smart optical engineer at placing mirrors around a body to bounce off rays in a way that would avoid the body itself. But obviously, those type of constructs that are actually very popular these days also in the scientific literature are fundamentally limited in leaving shadows, in working only for certain set of observers. So these fundamentally are not true, what we would call really an electromagnetic cloak. If you really want to achieve something that transforms something reflective or absorbing into something or opaque in general, into something that is transparent, you would want to route the light rays around the object. But this inherently implies that if you want to preserve the amplitude and phase of these rays, you need to make them run faster around your object, such that they act as if they would go through the object. And that poses a problem of causality. So you can do that, but you are bound to do it over a limited bandwidth. To get things that travel faster than light in the background medium, you either have a background medium that is very slow, or you have a narrow band operation of these responses. So this works only for long pulses that are long in time, and therefore can catch up in some ways inside the medium. In fact, we've done experiments recently, actually. This was a paper that we published only last year, in which we demonstrated this fundamental limit of how much bandwidth can you afford in a material that supports faster than light propagation of signals before they become actually unstable, or they have other issues of distortion of the signals. So fundamentally, this is the issue. A small object, it's easier to go around without having to pay a price. But when you try to do it for a large object, then the only way to do it is for signals that are very narrow band, so very extended in time, and that limits you the functionality. The dream of making a full human-sized body transparent to visible light fundamentally incurs into this causality issue. So that is not something that I predict metamaterials will be able to address. It's much easier to go the Houdini way to, or what animals do commonly, for instance, camouflaging, right? Mimetically hiding into a background that is uniform.
So I'm curious, what are some of the questions that metamaterials research is grappling with right now? Something that struck me with when I was watching some of your previous media appearances was an anecdote that you shared sort of about your entry into this work, about negative refraction and how it was being argued, about whether such a thing is even possible. Are there any debates like that that are happening right now? And what are some of the technological implications?
Absolutely. Yeah, that's a great question. First of all, you are absolutely right. The boom of metamaterials research interest was this negative refraction, and there was a lot of debate at that time on whether this was possible. A negative index of refraction takes a beam of light that travels right to left, and as it enters the material, pushes it back left to right. And such a response also has an interesting kind of apparent violation of causality, because if you think of a wave packet, the parts of the signal that are on, if I'm going in this direction, the signals that are more on this side have to travel slower than the signals that are on the opposite side. They have to do more wave, more path. And that was a big issue for several scientists. It was actually very interesting debate that was resolved over time. First of all, there were experiments demonstrating this, and now we understand why and how it happens. Basically, the bottom line is that there is a fundamental limitation on dispersion of these materials, on how the materials have to change their response in frequency and even in terms of angular response. Interestingly, even today, by the way, there are some small pockets of communities that are still fighting this type of responses, and in some ways are not believing them, even if the vast majority of scientists these days, with so many experiments and so many demonstrations in many different realms of frequencies of even wave phenomena, have been able to demonstrate this. So this is a settled argument. But you're right, over and over, given that we're pushing the boundaries of classical wave physics, there are debates, and actually these debates typically are actually very instructive. They actually help push the boundary forward. The initial idea is typically simplistic, and within these debates, we actually understand better what's going on in the process. I would say today one argument that is actually quite interesting is around the new field of time metamaterials. I can tell you very briefly what this is about. All these metamaterials technologies are based on structuring in space a material. And the idea is that when you have these tiny nanoscale interfaces that interact with waves, that they create as a collective scattering phenomenon a new form of wave interaction. So that they can structure a beam, they can steer it in unusual ways, or they can transform it in powerful ways for many technologies. Now, the field of time metamaterials is trying to extend this idea to temporal interfaces. What does it mean, having a temporal interface? In the same way as a spatial interface is fixed in time and has a sharp boundary in space, a time interface is a phenomenon for which the material properties of the properties of a material in terms of electromagnetics or acoustics are abruptly changed in time, uniformly in space. So rather than having something fixed in time but with a structure in space, now we have something that is fixed in space but abruptly changes in time. Over 60 years ago, there has been a lot of theoretical work trying to explore what happens to a wave when it meets a time interface. Basically, the wave is traveling in a material, and suddenly the material changes its properties. Let's say the electromagnetic property, the index of refraction and impedance. What happens is that the wave experiences a phenomenon similar to the spatial interface, in which it's refracted in time and reflected in time. And what this means is that a wave packet gets transformed in frequency. The spectrum of frequencies is abruptly transformed into new frequencies, and it's also time reversed. It coupled to negative frequencies. That implies that the signal is reversed in time, starts going in the opposite sequence as it was before. Still obeys causality, it still happens in the future, but it's reversed. It's as if in a conventional echo phenomenon, if I talk in front of a spatial boundary, like a mirror, I hear my voice in the same sequence as I have spoken. But if my voice actually meets a time interface, it's suddenly time reversed, and I would hear the echo with a reverse, played in reverse. Now, people have started playing with this phenomenon in regimes in which it's very easy to create time interfaces because the waves go very slow. So the first experiment of this type was for water waves. Water waves go extremely slow. So you can just apply a kick to a bath, and the water wave indeed gets time reflected. And they demonstrated, the group of Matthias Fink and his colleague in France have demonstrated this time reflection of water waves. Few months ago, we were the first to demonstrate time reflections for electromagnetic waves. And we did it for radio frequencies. And that created a lot of interest because also it has a lot of potential opportunities for applications. So we showed that you can send a signal in a material or in a metamaterial and abruptly change its impedance and index of refraction. And what you see is both a very efficient phenomenon of frequency conversion. The frequencies get all translated to new frequencies abruptly, and also time reversal, that the signal you sent in gets played in reverse in the new wave. But now the big question is, can we achieve this type of phenomena in optics? And optics would have so many other interesting implications for imaging, for instance, in which you can refocus a laser source into, or even a broadband source into its focus by inverting or time reversing its propagation. The challenge is that optical frequencies oscillate so much faster than the microwave frequencies, kind of radar or radio signals that we used in our experiment, that you need material responses much, much faster than what we were able to use, and very different mechanisms. We used switching technology that is very efficient for radio waves, radar, or wireless signals, communication signals. But for optics, such an instrument like a broadband switch is very difficult to achieve. And there is a lot of debate today on initial experiments in this sense, and if it is even possible to switch a material response so fast in time to create a time reflection. There is also a whole new field starting of time crystals, in which applying this type of time interfaces sequentially in a periodic fashion would realize the analog of a photonic crystal, typically realized through periodic spatial interfaces, but now in time. And this has also a plethora of other interesting applications for optics. But again, to be able to enter into this very interesting regime of periodic time interfaces, you need to be able to switch up and down very fast the response of a material. And the ongoing debate is it even possible to think that the material can switch its response sufficiently strong and sufficiently fast to engage with an optical wave? So this is an interesting ongoing debate. It's a fundamental in terms of material science, in terms of wave physics. There may be some fundamental issues in what can be actually achieved as the frequencies go up. But the good news is that already we have observed this phenomena at lower frequencies, and there is clearly like a smooth transition going from microwaves to optics. In our group, we're now looking into moving in the direction, like going up in frequency to see what type of phenomena can trigger these fast material variations.
Interesting. Now, with metamaterials and metasurfaces, it seems that the highest profile applications are in imaging. Companies like Metalens, which is the startup spun out of Federico Capasso's lab at Harvard, and NIL, excuse me, NIL Technologies have already begun commercializing Metalens technology. But most of the press surrounding Metalens has focused on, the miniaturization factor. Mostly, phones with no camera bumps, which, is nice. But, I think there's probably some more interesting opportunities than that, I would say. So looking at your work, there's a lot more interesting capabilities on the way for metamaterials enabled imaging, particularly with image processing. Could you tell us a little bit about that?
Absolutely. First of all, I'm all in favor of these commercial avenues. The field of metamaterials so far has been often criticized by the fact that we produce glossy papers and nice images in the lab, but there has not been as much of a push into the commercial world. So these great companies that are spanning off great labs are very good news for the whole field. And I'm also involved in a couple of commercial ventures in this area. I agree with you that a big push has been the idea of these metasurfaces, these structured interfaces that allow for miniaturization, compactification of optical elements. And the reason for that is that fundamentally building nanoscale structures, it's relatively easy on an aperture rather than in 3D in the bulk to build the whole material based on these nanoscale structures. So the metasurface technologies are the most accessible also in terms of building a large area. Now there are several companies that can feature this form of foundry for metamaterials, of printing metamaterials or metasurfaces in particular, like almost journal papers, like very fast process and large area. Yet, I think that just miniaturizing a lens becomes more of a niche demand, because lenses are so widespread and so efficient and so well designed, well understood over many, many years, that either the cost has to be low, or the application has to really require this miniaturization beyond the limits of classical diffractive optics. In our group, and also a few other groups across the world actually, have been interested in checking also what other things we can do in the context of metasurfaces in particular, that we can build over large area and can be more prone to commercialization. So beyond focusing or imaging, we've been showing these metasurfaces that can do image processing at the speed of light with no energy cost. This was a spin-off from a large funding grant from the Department of Defense, a MURI project that was aiming at MURI stands for Multi-University Research Initiative, and was the project was geared towards reducing energy cost for computing and signal processing. Today, in the civilized world, in across all countries, we consume an enormous amount of energy in processing data in data centers, and we typically rely on optical signals for doing that. So the question is, can we actually build infrastructures that can slash this energy demand that cannot be sustained at this level, at this growth level? So what we've been realizing is that one can build metasurfaces as passive thin film objects that can actually realize operations on images, on signals, and both in space and time. And this creates new forms of computing effectively that is very low energy in terms of energy costs, and also very fast. Latency is basically close to speed of light. Over the years, we've shown edge detection, we've shown other Fourier optics on very thin film. And what is surprising is that these are compatible with silicon films, so very much common materials compatible with CMOS technology, and also with large area fabrication. So one can think of integrate these into detectors, into optical systems, and realize some form of image processing in a fast and efficient way. We're now working even with companies very interested in integrating this into gadgets. You can think of sunglasses or windshields of a car, and start actually processing data in a way that doesn't require analog to digital transformations of conversion of signals, and processing, a lot of processing power to do these operations. We're moving now towards using this also for more complex problems like image classification, or for nonlinear transformations of processes, or even for neuromorphic operations. For instance, being able to detect changes in a scene, again, with just passive and energy efficient thin films. We're not necessarily saying that this will replace our personal computers, or is going to revolutionize the way in which we now process signals, but it's an interesting aid for especially these low-level operations that most computers actually do. And this has implications even for wireless communication systems, so lower frequency devices in which surfaces that bounce off signals can at the same time process the signals, the streams of data that we receive from users, for instance, to compensate for distortion, to apply Fourier transforms to the signals, or to sense what's happening around us. For instance, to see when users move around the surface. So this type of operations seem to be actually ready for prime time in the context of commercialization and of variety of optical and radio frequency systems.
Excellent. Now, as a final question, I'd like to ask you to tell us about something, or maybe a few things that you're excited about right now. And this could be anything, whether it's an initiative at one of your schools, a research work, or even something kind of trivial like a movie that's coming out.
Thank you. I mean, on the research side, I'm very excited about the prospects that are coming by merging the concepts of metamaterials with other fields of science. I was mentioning before this idea of time interfaces, and there are new material classes that seem to open to very interesting responses in terms of nonlinearities or speed of responses. There is this whole field is called polaritonics, of the engaging with light very strong material responses. This is something I'm very excited. I'm learning about, and we're doing experiments in this area, and I think it's a very exciting direction for many fields of science related to metamaterials. On the non-technical aspects, what I'm excited about is the surge of interest from the commercial point of view, and also from the point of view of international collaborations. One thing that I look forward to is recently we've been selected for this bilateral research initiative between US and Finland. It's a long-term project funded by two countries, and it's actually around the area of using this exotic wave matter interactions for wireless communications, to improve the way in which we are connected to each other. And it's not limited to just the physics or the engineering, but actually it goes beyond this, even to look at the ways in which these new technologies impact ethics or the psychology of users as they come about in the world. And what I'm particularly interested in is the fact that we are going to work closely with another country. I see that in the world these days there is a lot of geopolitical tension. We're all aware of all the awful events that are happening in various parts of the world, from the Middle East to Russia and Ukraine, to the tensions between superpowers like US and China. And I think instruments like this, in which research is actually driving these connections between countries, between cultures, should be very welcome. I think science can play a big role in trying to address these challenges that we see growing these days across the world. So I'm a true believer that science should be the instrument to bring together cultures, countries, nations, and I hope there will be more of these initiatives, and I look forward to working and exploring these interactions.
Awesome. It's always good to see, just people cooperating, between countries. It's really inspiring.
In some ways, it's getting more difficult, but I hope that these and other initiatives can help play a role in addressing this. Actually, a couple of years ago, we organized here at the City University of New York a workshop on photonics, but it was called the US Middle East workshop. And the idea was to actually bring together scientists from the Middle East, all countries in Middle East. We had people from Israel, but also from Palestine, from Egypt, Syria, Lebanon, and demonstrate that actually talking about science has no frontiers and can actually bring together different cultures and facilitate discussion, conversations, and push forward the technologies and the science, independent of barriers that can be cultural or can be political.
Right. I'm thinking of, I just saw something recently. There was a comedian talking about, different cultures and sort of, the idea of how we're so much more alike than we are different.
Absolutely.
And every culture will say, family is so important to me. Food is so important to me. And it's like, okay, well, you've just described everybody.
Absolutely.
We all love food. We all love our family.
I agree. Yes, and it's sad to see that we face more and more barriers, and there is a feeling about also, I think, propaganda between nations, between of how awful the other side is. But at the end of the day, actually, we, as you said, at the basic level, we are all human beings interested in similar issues, and I hope that more and more we learn to live together and to push together humanity to a better world.
With that, we conclude another episode of All Things Photonics. Thank you to our sponsors, to the technical staff behind the scenes, and to continued support from the Photonics Media editorial team. As always, questions, comments, thoughts, and ideas are welcome. Let us know how we're doing via email at allthings@photonics.com. All Things Photonics is available on all major platforms and on our website, photonics.com.